But now we have, let's say, a change in, let's say, supply to the right, or demand to the right. We might get a very quick change because the curves are relatively vertical. And then if we were to, let's say, re-equilibrate, we'd be back down to where we started. But once again, a relatively sharp shift down in the curve. So depending where these lines are crossing, you might get, let's say, different changes for, let's say, quantity and price, and the ratio of to them one to each other might be quite different. Now, another example is that not all supply and demand curves are nice smooth lines. They could be kinked functions. Now, if you're doing math, this is not a function because there's not one value of x for every value of y, or one value of y for every value of x. I forget exactly how a function is defined. But let's say, for example, we have a grading system, and instead of giving you grades from 0 to 100, I give you grades A, B, C, and D. And let's say I demand higher grades in all of you, and here it's kind of hard to say what's the supply curve and what's the demand curve, right? What's being supplied is more work, or what is being supplied is the teacher giving you grades. Depending on who you are, you could look at it differently, but let's just keep this simple for the moment. So let's say I demand higher grades and all of you increase, let's say, your effort. Okay, and so the work increases at a certain degree, but guess what? The grades didn't change. So let's say you're going from, let's say, a low B plus to a high A plus, maybe from an 87 to an 89. That's a 2-unit increase. But go from 87 to 89 is not really useful to you because, right, you're still getting a B plus. You're not getting any more oomph or any more payback for your increased effort. But if you have that same 2-unit movement from like an 89 upward, from an 89 to 91, right, that would move you up into A minus territory like this. Which means the same shift, let's say in quantity, can have a huge impact depending on how the supply and demand curves, whatever the functional shape of the supply and demand curves are. So let's talk about some of these specific models. The first one up is the auctioneer, and this is because this is the most basic of all the models. This is really what kind of Adam Smith had in mind when he was talking about the invisible hand, and this is kind of basically how the late 19th century marginalists, which were the group that added mathematics to economics, basically saw the world. And let's say, for example, we have a dating market. And our dating market is someone wants to go to prom, and he kind of wants to know what his value is, what is his value as a commodity, right? He wants to attract a female escort or one of the other girls in the class, but, right, some might like him, some might not like him, but he doesn't really care about this girl or that girl. He wants to know what his average value is for all the girls are. So let's say we're going to use Charlie Brown here. Charlie Brown wants to go to, let's say, the dance, and there are 5 unattached females, and all of them, the auctioneer says, okay, we're having a bachelor, auctioning off an escort, but he's going to take, let's say, the price from each of our 5 eligible ladies. Okay, you can see that all these different ladies give him different prices. Maybe Peppermint Patty gives him an 8, right, because she kind of likes Chuck. Marcy's kind of a nice girl. She might give him a 6, right? Maybe she's kind of 4-eyed, just like Mr. Brunelli, and maybe she can't attract, so she's going to see Charlie Brown as kind of more of a catch than others. We know about Lucy in the football. She gives him a 2. Frida is kind of a vain person. Maybe she gives 1. She's the girl with the naturally curly hair, and Charlie Brown is bald. She doesn't find that too attractive. And Violet might give him like a neutral score of a 5. And so this should add up, I believe, to 22 points. Divide that by 5, that means Charlie Brown's value is 4.4. Now, the auctioneer, of course, doesn't just like these specific one-number answers. They also want to figure out, for example, why does Peppermint Patty give you an 8? Why does Marcy give you a 6? Why does Violet Gray give you a 5? And what he's trying to do when he makes enough observations is, let's say, everyone has an equation in their head that determines whether they want something or do not want something. Some people like certain colors, some people might like certain cars. Different things appeal to different people. And we could break these down into nice little equations like you see here in the yellow bubbles. And from that we could actually kind of figure out what is it about Charlie Brown that makes him attractive. And we can maybe break this down to 3 areas: outer beauty, inner beauty, and how much cash he has in his wallet. Now, all these different ladies might put like a different value on the relative value of outer beauty. But if you solve for all their equations together, we can find out that their estimate of Charlie Brown's outer beauty is a -1. And remember, if you're bald in 5th grade, life is tough. He's got a kind of paunch there. Outer beauty is not his thing. But you also know you're a good man, Charlie Brown. He's a nice guy, always trying to do the right thing. You'd want him as your friend. His inner beauty is relatively high. It's a 5. And let's say his father's a barber, doesn't make that much money. We'll call, let's say, his cash in his wallet as a relatively low number 2. And you can see each lady has a different equation, which is the value they put on all these different qualities, right? Frida might put an 8 on outer beauty because she always talks about her naturally curly hair, and that's how she sees the world. Marcy might put a higher value on inner beauty because she's kind of, let's say, this intellectual type, and she writes poetry in her room at night or confides her thoughts to her diary, so she really puts a high value on inner beauty. And someone else might put, let's say, a relatively high view like Violet Gray. She might put a really high value on how much money Charlie Brown makes. And so these are all different. Everyone can put different values on that, but the average value by solving for all the equation gives you A equals -1, B equals 5, C equals 2, and you could say these are the objective scores to Charlie Brown's values in these different dimensions. Now, what the auctioneer does is takes all this information, and he uses matrix and linear algebra, and yes, you did learn this in school. And you could take all these equations and put them into a matrix like this. So Frida's matrix, if you go across horizontally, remember A, B, and C stand for outer beauty, inner beauty, and cash in his wallet. And that makes all 3 columns, and then each lady, if you just take the coefficients of all their equations, you can kind of arrange them like this. So Frida's would be 8, 1, 2, Lucy's 4, 1.5, Marcy 1, 2, -1.5. Okay, and you can solve for this equation, and this would give you basically the demand function for Charlie Brown. Now, we could also break these down. For example, this 8 by Frida, this might be a matrix of equations too. For example, all the different things that go into outer beauty for Frida. Or this 2 here for Marcy might be all the different things that go into inner beauty for Marcy. Right, we could have an equation. And this is just for Charlie Brown. Now, if we were doing this for many, many different guys and many, many different girls, right, we could have all the different demand functions for all the different guys by all the ladies in the high school class. Okay, this is a big equation. But fortunately, our auctioneer, can solve for all these equations. And we have all the ones for people's demands and all the equations relating to the cost of different supply, different things. For example, how many minutes do you have to comb your hair in the morning? How much time does it take? The genetic functions, the shape of your nose, or what have you. What do you have the most recent model of eyeglasses or not? So what this Walrosian auctioneer is basically sucks the information out of all our heads by observing what we do, and it takes all these individual consumer demand functions and all the individual producer supply functions, aggregates into these large matrices, okay, and then solves for like A, B, and C like we did before, okay, and from that we set the matrices for all demands, aggregate demand, and the matrix for aggregate supply, set them equal to each other, then solve for that, and then you come up with a number. And so fortunately, as I said, he has a big calculator, he loves math. This is a lot of equations, but the market, the invisible hand, basically does it on its own. It's constantly recalculating and recalculating, but eventually it's going to set aggregate demand equal to aggregate supply, and this is going to lead to one price. There's going to be one price for Charlie Brown after all the ladies have weighed in with their individual demand functions. Now the assumptions here is that it's determinate. There's only one price, we'll solve it, it's fixed. There's only one unique solution, and the system is basically in equilibrium, right? We set aggregate demand equal to aggregate supply, which is saying, look, the system is basically in balance, or if it's not in balance, it soon will be, and all we have to do is assume that's in balance, and then we can solve for all the different variables. We can solve and for the variable of the one price. It also basically assumes that this auctioneer is relatively a nice guy and is not going to charge us for all his services, and his calculator doesn't need batteries and what have you, and so all we have to do is what's inside the equations, and from that we'll get the equilibrium. So that's basically the auctioneer model. As I said, this basically portrays supply and demand as a system of, equations, and you solve for these equations, and if you have enough time, you like math enough, you'll solve for all the equations and you'll get answers. But for the models coming up, I think we need to think a little bit differently, and we need to think of this in terms of Einstein's theory of relativity, and that, for example, gravity is not simply a force. It's not like 9.8 meters per second, okay, pulling you down to the center of the Earth, but that time and space is a continuum, and what gravity and other forces are ripples in this time-space continuum. And to bring it to prices in economics, we have to see, for example, these prices as pinballs that are riding over these surfaces. And so a point of equilibrium is kind of like a depression, because the pinball will get stuck in that depression and it won't want to move, but sometimes it's stuck on top of a ridge and it'll roll downward as well. And for those of you that are cat people, this is maybe another illustration. When you woke up this morning, the cat found its equilibrium, right, in one of the depressions in your comforter. And I'll just read this out loud. I is your time-space continuum, upsetting all your gravity and quantums and stuffs. Okay. So on to the other models that are more kind of, let's say, this Einstein rather than Newtonian physics. The first one is the rocking horse model, and I just start with this one because this is a fairly basic and one of the older ones. We have all had a rocking horse, right? The rocking horse basically doesn't move if we don't touch it. Bodies in motion will tend to stay in motion. Bodies not in motion will stay at rest. But let's say we take a big shock. Boom. And our rocking horse rocks back and forth, back and forth. Now eventually, right, this shock is going to wear off and the rocking horse will stop moving. Okay? Now it might be oscillating or rocking back and forth, but it's basically rocking back and forth over a constant point. And as a result, that's kind of the long run equilibrium here. Eventually we know if we don't hit the horse will balance on its skids and it won't move. Now the key thing here is not, let's say, the whole horse, but kind of this curved skid, right? It has a fulcrum here at the bottom and it rocks back and forth on top of that fulcrum. But if you think of the time-space continuum, right, this is kind of like a depression in that time-space continuum, and that pinball, the pinball will settle right here in the bottom. So for example, let's say we had that same big shock, right? That's going to move and this gets back and forth, back and forth. And we can think of this price as like that little pinball sitting in the bottom of this, let's say, little depression here, right? And when there are shocks, right, things that shake this time-space continuum, the price is just going to rock back and forth, but eventually that price is going to settle down at the bottom of this depression. And this is basically what the rocking horse says happens. The economy is basically in balance, right? It's in a depression, the prices are at the bottom, unless you shake it or you drop it or you move it. And those things that happen in the world, famines, wars,